Oh, that looks so proper. Oh my goodness. Okay, so the objective of this lab is to construct a simple computer program that will calculate the speed and distance fallen by a fallen body using numerical integration. What? Alright, so when we're talking about stuff falling, we gotta talk about the differences between free fall and non-free fall. In this situation, I'm going to define the coordinate system as positive y being the downward direction. Coordinate system. Oh yes, a whole lot of defining happening. Alright, so we've got free fall, where an object's just falling, right? And the only force acting upon it is its weight. And then we've got non-free fall, where it's a force acting upon, has weight, and then this other force, R. So the main force, the only force acting on free fall is gravity. There's two forces acting on a non-free fall object, that is gravity and air drag. Alright, given to us by R. Okay, so R is equal to K times velocity. This is only at low speeds. Okay, so speed of light, no, don't even go there. Don't even go there. Alright, so this magical K is a constant that is dependent upon the shape of the object that is falling. That's a funky H. The shape of the object that is falling and the viscosity of the liquid that it is falling through. Yes. Yeah. Through. This is always a confusing word. Through. It's up to you. Yay. Okay, so say we have a box falling with, R. May not have the same K value as a sphere falling with the same even mass. And say we've got these objects now falling, same objects, falling through jello. Oh, there it is, jello. Okay, so same box, now it's just in red. Yeah. And again, the same sphere in red. They'll have different K values because they are falling, the viscosity of the fluid in which they are falling through is different than that of air. Okay, so now let's talk some math about falling. Yes, we're going there. Okay, so the main thing we're looking at when stuff falls is Newton's second law. The sum of the forces is equal to mass times acceleration. In a free fall, that acceleration is equal to g, the acceleration due to gravity, 9.8 meters per second squared. All right, that's it. Now, when we look at a non-free fall situation, the sum of the forces is, again, mg minus r, because r is moving in the opposite direction. And so let's make things fun. And ma is equal to mg minus r, and because we want r to show its true colors. I mean, come on now. Why are you going to hide stuff from us? So we've got this wonderful equation here, and now we want to cancel out our masses because really, who likes mass? Come on now. So we're going to divide everything by m. But now we still have a mass on this side. So our equation becomes acceleration is equal to acceleration due to gravity minus this magic k over m times velocity. And now it's magical because it's brutal. Okay, so what we want to do is, using this equation, find position and velocity as a function of time. But let's explore how awesome this equation is and all the things we can do with it. So say k is equal to 0, then that whole thing goes to 0 and we have free fall, a equals g. Now say k isn't equal to 0, the acceleration of the object, as the acceleration of the object decreases, velocity increases, and then the world ends! Yeah, that's all I could come up with. Okay, so as the acceleration of the object decreases and the velocity increases, basically what's going to happen is our air drag is going to equal the weight of the object, and so we're going to end up with zero acceleration. This doesn't mean that the object's going to randomly stop mid-air. No, all it means is that it's going to have reached its terminal velocity. It's going to stop accelerating and just fall. Right? Okay, so now let's get to the good stuff. Numerical integration. This is how we're going to be looking at the trajectory of the fall. We're going to Oh, look, handy dandy. The way to approximate an object's trajectory based off of estimations of average acceleration and velocity in small increments of time. Okay, so what we want to do is look at average acceleration first. No, just kidding. Average velocity first. So v is equal to delta x over delta t. Delta x is equal to x final minus x initial. That's all position over delta t, which is a time interval. So what we want to do is we want to solve for that final position of x, the falling object that's falling. And that gives us this equation here, the initial position plus velocity times delta t. This gives us the position as a function of time. What? That's exactly what we wanted. Alright, so now let's do some plug and chug and actually see what's going on. So we're going to give some values to some of these variables. So we're going to say the velocity is 5 meters per second, initial position is 0, and that time, delta t, time interval is going to be 1 second. So plug and chug and awesomeness, and then what happens? Well, then we get 5 meters. So after 1 second of falling, our object will have fallen 5 meters. What? Oh yeah, oh yeah, oh yeah. Okay, so this value for the final position will allow us to move on with all of the falling stuff. Yeah. So basically we can find the next position after another second. Now, just real quick, the math behind the time. So say we start at 0, everything's 0. Now to get to the next time interval, delta t is equal to time final minus time initial. And so we're going to solve for time final, the final time, and it's the same way as solving for the final position. We're going to go through this same process again, and then to get to the next time that will be looking at, we'll do 1 plus 1, the time interval plus the last time, and we'll get 2. Hey! So now let's go back to position. So the final position is just plug and chug and have some good times. Yeah! And so we find that 5 meters plus 5 meters is equal to 10 meters. So after 2 seconds, our object will have fallen 10 meters. I see a pattern, just a little bit of one. Oh, what's going to happen next? 15 meters. Yay! Oh, this is so exciting. This is so exciting. But we can continue that table later. So now let's look at average acceleration. So can you guess what this is going to give us? Velocity! So just as position is changing, so is velocity. And with this approximation, we can also get the velocity as the time continues. Okay, so real quick, side note. So as the time interval is smaller, we get better approximations on what exactly is happening in the fall. Congratulations, you now speak some math. Isn't that awesome? Oh, master. Headbands needed. Mwah. Okay, so basically with the rest of the lab, now that you have theory of what you will be doing, you are going to be provided with a computer program that will be in MATLAB. This is the first year we're using MATLAB in all of its awesomeness, so we're going to go ahead and explain it to you in lab. But now that you know the math that's happening, literally all you have to do is look at the computer program, change things around, see how it runs, and get some awesomeness coming out. Aren't you excited? That's the setup. That's the equipment that you'll be using. Right, easy for me. And that's it. So yeah, I hope you guys have a great week and that you enjoy this lab. It's a little bit different lab than we've been doing, so I hope you enjoy the change of pace. Okay, bye-bye.